A Nobel Prize winner looked at the data from the James Webb Space Telescope and said 4 words. 4 words that no one in cosmology has been able to publicly refute since he said them. This is not our universe, not a metaphor, not a philosophical provocation. A statement about the data, about what the telescope actually found when it looked deeper into space than anything built by human hands has ever looked before. Cosmologists have been unusually quiet since those words were spoken. Not because they think he is wrong, because they do not know how to explain why he might be right, and what it would cost us if he is. This is where we are going. Not to reassurance, not to a tidy resolution. We are going to follow the data wherever it leads, through the physics that breaks, through the mathematics that doesn't close, through the questions that were supposed to be settled and turned out not to be. The telescope is still running. The data is still arriving. And the picture it is building does not look like the universe we thought we lived in. John Mather spent 20 years measuring the cosmic microwave background, the faint thermal glow left over from 380,000 years after the beginning. His instrument, COBE, measured temperature variations to 1 part in 100,000 and found them exactly where the standard model predicted. The Nobel Committee gave him the prize in 2006, not for proposing a theory, for confirming one with a precision that left no statistical room for doubt. He was the man who weighed the foundation and certified it. So, what does it mean that this specific man is the one who said it? Then Webb started sending data. And Mather said 4 words publicly. This is not our universe, not in a paper, not in a peer-reviewed journal where every word gets stress-tested before publication. In a public forum. No error bars, no caveats buried in a methods section. 4 words. Think about what it means when the building inspector who certified the foundation is the one standing outside saying something is wrong, not a competitor. Not someone who always thought the foundation was suspect. The person who signed off on it. Anyone else saying the model fails is a critique. Mather saying it is something closer to a confession. He is not attacking Lambda CDM from outside. He built its strongest wall and is now saying the structure does not match what he is looking at. The field's response was not a press conference, not a coordinated rebuttal. The response was the same careful language that started appearing in papers. Unexpected, difficult to reconcile, challenging our current understanding, which is how physicists say, we do not know what to do with this yet. I find that specific silence more informative than any counter-argument would have been. What does it mean that Mather's 4 words have not been publicly refuted by anyone with comparable standing? And what I cannot move past is this. He did not say the data is wrong. He did not say the instrument failed. He said the universe. That is where this begins. In February 2023, Ivo Laber's team published a paper in Nature. 6 galaxies. 6 galaxies Webb photographed in the earliest slice of cosmic time, 500 to 700 million years after the beginning. Each contained stellar mass equivalent to tens of billions of suns. Galaxies that massive, that early, should not exist. Not approximately, should not exist at all. Laber's team estimated these 6 objects together held more stellar mass than the entire observable universe was supposed to have produced by that point. Mike Boylan-Colchin at UT Austin read the paper the same week. He used 2 words, universe breakers. His analysis showed that even one of these galaxies taken at face value requires star formation efficiencies that violate how matter physically collapses under gravity. You cannot form stars faster than gravity allows. Gravity has a speed. These galaxies had apparently ignored it. What does it mean that the first deep field images Webb returned contained objects that break every simulation built in the last 30 years? Teams went looking for the mistake. Different instruments confirmed the redshifts. Spectroscopic follow-up through 2023 confirmed the masses. The galaxies were real. They were where Webb said. They weighed what the photometry said. At that point, the question changed. It stopped being, is the instrument wrong, and became, what does it mean that the universe contains objects its own history says cannot exist? Picture a geologist who cores a sample from what he is told is recent sediment. The sample comes back with layered complexity that takes 1 million years to form. He tests the core 3 different ways. Same result every time. At some point, he stops questioning the instrument. He starts questioning the timeline he was given. That is where Webb put cosmology by the end of 2023. The cores are real. The timeline does not fit. Now you have Mather saying, this is not our universe. And Boyle and Colchin's data explaining why. 2 people, 2 directions, 1 conclusion. What does it mean that the field's most credentialed validator and its most precise stress tester arrived at the same place in the same 18 months? And I find I cannot look at that and call it a coincidence worth ignoring. The defense that gets offered first is always the same. Maybe the galaxies formed faster than our models allow. Maybe early star formation was more efficient than assumed. Maybe we are underestimating how quickly the first structures could collapse under favorable conditions. These are not unreasonable starting points. They are the correct scientific response. Stress test the assumptions before concluding the framework is broken. So physicists stress tested them, systematically. Step 1. Push star formation efficiency to its theoretical maximum. In standard models, roughly 10% of available gas converts to stars in a given period. Some researchers tried models with efficiencies approaching 100%, every available atom becoming stellar fuel immediately. The galaxies Webb is finding still should not exist at the masses they display. Step 2. Adjust the dark matter halo models that seed galaxy formation. Dark matter halos collapse first and provide the gravitational wells into which ordinary matter falls. Researchers modeled the most extreme halo concentrations that current dark matter physics permits. Still insufficient. Step 3. Introduce exotic early physics. Population 3 stars that are thousands of times more massive than any star alive today, burning through their fuel in millions rather than billions of years. Better. Still not enough. Think about it this way. You need to fill a swimming pool using a garden hose. The pool requires 1 million gallons. You have 6 months. You run the hose at full pressure every second of every day. You are still short by a factor of 10. Replacing the hose with a fire hydrant helps. But the pool still does not fill in the available time. That is the situation with early galaxy formation. Every efficiency gain available inside the existing model moves the numbers in the right direction. None of them move them far enough. I think this is the specific moment where the standard scientific instinct, find the error, adjust the parameter, refine the model, starts to fail. Not because the instinct is wrong, but because the gap is not the kind that parameter adjustment closes. What does it mean when every available adjustment moves the model closer to the observation without ever reaching it? At some point, a model that requires increasingly extreme adjustments to approach a result is no longer explaining the result. It is accommodating it. The first thing a careful scientist does with an impossible result is look for the mistake. Webb's calibration was checked against multiple independent standards. The redshift measurements, the technique that establishes how far away and how early a galaxy exists, were verified using both photometric and spectroscopic methods. Photometric redshift estimates colors and infers distance from the color pattern. Spectroscopic confirmation measures actual emission lines in the galaxy's light, direct, unambiguous, hard to fake. The 2023 spectroscopic campaigns took the most extreme photometric candidates and ran the spectroscopic test. The results did not shrink the sample, they confirmed it. Every door that could have admitted a systematic error was tested. None of them were open. This matters because the history of astronomy is littered with instruments that found something revolutionary and turned out to have a calibration problem. The faster-than-light neutrino result in 2011, a loose fiber optic cable. The BICEP-2 gravitational wave signal, foreground dust, inadequately subtracted. Science has a working mechanism for catching its own mistakes. It works. It caught those. It looked at Webb's early galaxy results and did not find a mistake to catch. What it found instead was the same answer, returned more precisely with every new observation. The teams looking for the error were motivated to find it. Resolving a calibration problem would have been far more comfortable than what the data was saying. They could not find it. You are a cartographer who has spent 30 years making maps of a continent. Every instrument check passes. Every independent survey confirms the coastline. And then one day you compare your map to an older map and discover that the continent is in a completely different place than you assumed. Not because your instruments were wrong, but because the reference frame you calibrated them against contained an error that none of your instruments could see. That is the category of problem Webb may have surfaced. Not a measurement error within the framework, but a question about the framework itself. What does it mean when the most rigorous follow-up produces the same answer as the initial observation? What does it mean that the gap between the data and the model grew larger with each independent confirmation rather than shrinking? And the thing I keep returning to is this. The scientific process for finding errors worked perfectly. It found no errors. That is not a reassuring result. That is the result that means you are no longer dealing with measurement uncertainty. You are dealing with reality telling you something the model said could not be true. There is a number. It describes how fast space is expanding, how quickly the distance between any 2 points in the universe grows with time. For most of cosmological history, pinning it down was considered the field's central practical challenge. Not because the concept was unclear, but because measuring it accurately enough to matter required instruments that did not exist yet. Two different methods were being refined simultaneously. The assumption was that as precision improved, the two methods would converge. The opposite happened. Picture two surveyors hired to measure the same river. One measures from the source, working downstream. The other measures from the mouth, working upstream. They use different equipment, different teams, different techniques. When they finish, their measurements of the river's total length should agree. If they disagree by 0.5%, you recalibrate. If they disagree by 9%, after both teams have rechecked their instruments 3 times, you stop questioning the instruments. You start wondering whether both surveyors are measuring the same river. That is exactly where cosmology found itself. The Planck satellite measured the expansion rate from the cosmic microwave background, the thermal relic of the early universe, and got 67.4 kilometers per second per megaparsec. Distance ladder measurements using Cepheid variable stars and Type 1a supernovae got 73.9% apart. Both measurements internally consistent, both independently verified, running on the same physics, measuring the same universe, producing numbers that cannot simultaneously be correct, if that physics is one thing. I find the 9% gap more significant than it sounds. After decades of precision refinement with the best instruments ever built, a discrepancy that grows rather than shrinks is not a measurement problem. What does it mean when two verified measurements of the same quantity give different answers? Which universe is each method actually measuring? And if the answer is the same universe, why are the numbers different? And what I find genuinely difficult to set aside is the direction this points, not toward a measurement problem, because measurement problems produce inconsistency within a method, not consistent disagreement between methods. This points towards something happening in the physics itself, in the gap between the early universe and the late universe, in the space where our model connects the two. Something is wrong. Now find it. That was the assignment that the cosmology community gave itself around 2018, when the statistical significance of the Hubble tension crossed the threshold where ignoring it became professionally indefensible. Every major team took a run at closing the gap, None of them closed it. Step 1. The Cepheid calibration. Cepheid variable stars pulse at a rate tied to their intrinsic brightness, a reliable relationship that allows astronomers to use them as standard candles. But what if the relationship breaks down in dense stellar environments, where crowding might contaminate the photometry? Teams rebuilt the Cepheid distance ladder from scratch using different anchor stars, different calibration techniques, different software pipelines. The gap survived. Step 2. The Planck CMB analysis. The CMB-derived expansion rate depends on assumptions about the primordial power spectrum, the initial distribution of density fluctuations in the early universe. Independent teams reanalyzed the Planck data with different assumptions about early universe physics. Some models shifted the CMB-derived number slightly. None closed the gap cleanly without introducing new inconsistencies elsewhere. Step 3. New physics in the early universe. Early dark energy, a brief burst of additional energy density in the first 100,000 years, could shift the CMB-derived value upward toward the distance ladder result. Models were built and tested against the full dataset. They helped. They did not close the gap. They moved it. In 2023, the team that had spent decades building the distance ladder switched from the Hubble Space Telescope to Webb for their Cepheid calibration. Webb is sharper. The calibration got cleaner. The gap did not close. It sat at the same value it had been holding for 5 years of increasingly precise measurement. Think about a locksmith called to open a stuck door. He tries every key on his ring. None work. He files new keys to different tolerances. None work. He replaces the lock mechanism. Still nothing. At some point, after the keys, after the mechanism, after the hinges, a good locksmith stops asking what is wrong with the keys. He asks whether it is the right door. 10 years of failed Hubble tension fixes are the keys. The door they were supposed to open is a universe with one consistent physics from early to late. That door has not opened. What does it mean that 10 years of dedicated effort by the best equipped observational teams in history produce no resolution? What does it mean that the gap grew more statistically significant with each new precision campaign rather than less? And here is the position this creates. A discrepancy that survives every systematic check, that grows sharper with better instruments, that resists every proposed internal fix, is no longer a measurement problem. It is a physics problem. There is a second anomaly hiding inside the first. The light from early Webb galaxies is not just old, it is chemically specific. Spectral lines, the fingerprints of individual elements encoded in the wavelengths a galaxy absorbs and emits, tell you what the galaxy contains. And what Webb is reading in the spectra of these early structures is not what the first stellar generation should have produced. Carbon, oxygen, iron. These elements do not exist in a young universe. They are manufactured inside stars, fused from hydrogen and helium over millions of years of nuclear burning, then scattered into the surrounding gas when those stars die. That scattered material collapses into the next stellar generation, which is born chemically richer than the first. This process is called nucleosynthesis, and it has a pace that physics sets and chemistry cannot override. You cannot inherit a library from grandparents who have not yet been born. You cannot build a city from materials that have not yet been quarried. The chemical complexity Webb is detecting in these galaxies requires ancestors, stellar generations that lived complete lives before the galaxy Webb is observing had time to form, which means the universe needed to complete multiple cycles of stellar birth and death inside a window that the standard timeline barely had room for one. Think about sediment. A river delta forms over tens of thousands of years as sediment accumulates, channels shift, and the system reaches its characteristic branch structure. The layers at the bottom record the beginning. The layers at the top record the present. Now, imagine finding a river delta where the deepest sediment is only 500 years old, but the delta has the layered complexity of something 10,000 years in the making. The layers are real. The dates are real. The timeline connecting them is not. That is the chemical situation Webb is documenting in the early universe. The complexity is there. The time required to produce it is not. What does it mean that the mass problem and the chemistry problem share the same root? Not enough time. What does it mean that two independent observational signatures, measured by different instruments using different techniques, both point at the same broken variable? And what I think is worth sitting with is this. If the timeline is wrong in the early universe, it was wrong before Webb looked. We have been operating with an incorrect timeline for decades. I find the chemical evidence particularly hard to dismiss because it does not depend on a single technique. Mass estimates use photometry. Chemical abundances use spectroscopy. Two independent lines pointing at the same impossibility. In 2019, Adam Rees, Nobel Prize 2011, for discovering that the expansion of the universe is accelerating, said something that got almost no attention outside the field. The Hubble tension had passed 5 standard deviations, 5 sigma. In particle physics, 5 sigma is the threshold for declaring a discovery. Rees was not announcing a discovery. He was announcing that the disagreement between two measurements of the same number had grown too large to attribute to chance. He used a specific phrase, "Something is fundamentally wrong." That was before Webb launched, before LABA's 6 universe-breaker galaxies, before DESI measured 6 million galaxies and found dark energy shifting. Rees was describing one crack in 2019. By 2024, there were 4. Different instruments, different phenomena, different teams, each pointing at Lambda CDM and finding it insufficient in a different place. One crack is a question. 4 cracks in 4 different walls of the same building are an answer about the foundation. A structural engineer who finds cracks in 4 load-bearing columns on the same day does not investigate each crack separately. She stops asking what is wrong with the columns. She asks what is wrong with the ground they are standing on. The early galaxy problem, the Hubble tension, the DESI dark energy result, the Hercules Corona Borealis Great Wall, they are 4 columns. The ground they share is Lambda CDM. What does it mean that a Nobel laureate flagged a fundamental problem in 2019, and by 2024, the list of fundamental problems had grown rather than shrunk? What does it mean that every precision measurement run since then sharpened the anomalies rather than resolved them? And I keep returning to Rees's specific words. Not something is wrong with a measurement, but something is fundamentally wrong. He was more right than he probably wanted to be. Something is wrong with the foundation. Here is what the foundation is. Lambda CDM, lambda for the cosmological constant, the term in Einstein's equations that represents the energy density of empty space, the thing accelerating the expansion of the universe. CDM for cold dark matter, the invisible mass that provides the gravitational scaffolding on which visible structure forms. Together they describe a universe that is 5% ordinary matter, 27% dark matter, and 68% dark energy. A universe that expands at an accelerating rate and produces the large-scale structure we observe with a precision that was, until recently, the envy of every other field in physics. Lambda CDM is not a hypothesis, not a working model under active revision. It is the operating system of modern cosmology, the framework inside which every simulation, every prediction, every statement about the universe's past and future is computed. The line between the model and reality blurred because the model kept working. Observation after observation confirmed it. The CMB power spectrum, galaxy clustering statistics, baryon acoustic oscillations, the abundance of light elements. The model worked so consistently that the question of whether it was accurately describing reality or just approximating it very well stopped feeling urgent. Consider what happens when a computer's operating system has a hidden flaw. Every application running on it functions normally, every file opens, every calculation completes. The flaw is invisible as long as no process demands something the OS was not built to handle. Then, one program makes an unusual request. The crash does not look like an OS failure. It looks like a problem with that one program. You reinstall the program. It crashes again. You try a different program that makes the same request. Same result. At some point, the crashes stop pointing at the programs. Lambda CDM is the OS. Webb is the program making the request. The OS was not built to handle. Now, fail every one of those tests in succession. Early galaxies at the wrong masses, Lambda CDM fails. Chemical complexity at the wrong epoch, Lambda CDM fails. Expansion rate disagreement between early and late universe, Lambda CDM fails. Each failure alone might be a detail. Together they are a verdict on the framework producing them. I think what matters here is the specific location of the failures, not at the edges where new physics is expected, but in the predictions the model was most confident about. That is not how details behave. What does it mean that the framework describing everything fails at precisely the things it was most certain of? What does it mean that it is not a theory you can fix by adjusting a parameter? It is a framework you can only fix by asking what kind of framework should replace it. And what I keep returning to is that nobody has answered that question yet. The verdict is in. The replacement is not. The dark energy spectroscopic instrument mapped 6 million galaxies over 5 years. That is not a sample. That is a census. DESI measured the three-dimensional distribution of galaxies across cosmic history, looking for baryon acoustic oscillations. The fossilized imprint of sound waves that moved through the early universe and left a characteristic scale in the clustering of matter. This scale works as a standard ruler. Measure it at different distances, at different moments in cosmic history, and you can reconstruct how the universe expanded at each of those moments. A frame-by-frame record of the expansion history. What DESI found when it assembled that record is that the lambda in Lambda CDM, the cosmological constant, the fixed number Einstein's equations assigned to the energy density of empty space, does not behave like a constant. Its effective value shifts across cosmic time. At some epochs stronger, at others weaker. The data published in 2024 across multiple papers by an international collaboration of hundreds of physicists shows a preference for dynamical dark energy, a vacuum energy that evolves rather than sitting fixed throughout cosmic history. Think about a ship's navigator using a compass that gives consistent readings for years, then suddenly starts drifting. Every calculation made on the assumption of a fixed compass is still accurate for the period when the compass was stable. But every calculation made to project the ship's future position, or to reconstruct where it was before the compass was installed, is now wrong by an amount proportional to how much the drift matters. Lambda CDM is that compass. 6 million galaxies worth of measurement is the moment the navigator notes the drift. Every prediction Lambda CDM made about the future of the universe, every reconstruction it offered of the universe's past, was built on a number that was not what it appeared to be. What does a dynamical dark energy mean for every cosmological model built before 2024? What does it mean that the most precisely measured constant in cosmology turns out not to be constant? And what I find important is this. We did not know the constant was drifting until we had enough data to see it. Everything calculated before that discovery was built on a number we misread. The cosmological constant controls the fate of everything. Not in an abstract sense, in the sense that every serious model of how the universe ends is built on assumptions about what dark energy does over trillion-year timescales. Change what dark energy does, and you change the ending. Change it enough, and the ending we predicted becomes unrecognizable. The standard picture assumed a fixed lambda and produced a specific trajectory. The universe expands forever at an accelerating rate. Galaxies drift apart until no light from one can reach another. Stars burn out. Black holes evaporate over incomprehensible timescales. What remains is cold, dark, thermodynamically exhausted. The heat death. That picture required lambda to remain at its current value indefinitely. Lambda is not remaining at its current value. If dark energy grows stronger over time, if the drift DESI detected is in the direction of increase, the trajectory shifts. A sufficiently strong dark energy overwhelms every other force in sequence. It tears apart galaxy clusters. Then individual galaxies, then solar systems, then planets, then atoms. The Big Rip. A universe that does not fade into darkness but shreds, with the final moments occurring faster than the speed of light can carry a signal from one side of a proton to the other. If dark energy weakens and eventually reverses, expansion slows and turns back. Collapse. The Big Crunch. A universe that ends where it began, or something like it. If dark energy oscillates, the trajectory becomes something current models cannot reliably predict. 3 different endings, corresponding to 3 different behaviors of one variable. The DESI data does not clearly select one. What it selects is instability, dark energy that is not where Lambda CDM said it was, and that may not stay where it is now. We were writing the final chapter of the universe based on a constant that was not constant. Think about a structural engineer who calculates the lifespan of a bridge, assuming the steel maintains a fixed tensile strength across all temperatures. The calculations are meticulous. The safety margins are built in. Every projection about when the bridge will need reinforcement, when it will reach the end of its service life, how many cycles of load it can handle, all of it rests on that fixed number. Now discover that the steel's tensile strength changes slowly over time, not by much. Enough to matter across decades. Every calculation downstream of that assumption is now wrong by a compounding margin. The bridge is not the bridge you calculated. Cosmology's projections about the fate of the universe are the calculations. DESI just found the steel changes. What does it mean that we projected the fate of the universe trillions of years forward on a variable that turns out not to be fixed? What does it mean that all 3 endings, heat death, Big Rip, Big Crunch, were calculated assuming the same constant that DESI is now showing is not constant? The chapter is not written. It has not even been outlined accurately. Dark energy has a name. It does not have an explanation. The cosmological constant appeared in Einstein's field equations in 1917, added by hand to prevent a static universe from collapsing under its own gravity. When Hubble demonstrated that the universe was expanding, Einstein removed it. When supernova observations in 1998 showed the expansion was accelerating, it was reintroduced, reinterpreted as the energy density of the quantum vacuum, the irreducible energy that empty space carries. Lambda returned. The explanation did not follow. Quantum field theory predicts that the vacuum should have an energy density. Virtual particles pop in and out of existence everywhere in space, each pair briefly borrowing energy from the vacuum before annihilating. The sum of their contributions produces a baseline vacuum energy. Physicists calculated what that energy should be and compared it to the cosmological constant we actually measure. The predicted value is somewhere between 40 and 120 orders of magnitude larger than the observed value. 10 to the 40th power. 10 to the 120th. The largest discrepancy between theoretical prediction and observational measurement in the history of physics. Physicists named it the vacuum catastrophe. The name is accurate. The solution does not exist. Think about a chemist who calculates how much heat a reaction should produce. She runs the experiment. The actual heat released is 100 billion times smaller than her calculation. Not a rounding error, not a missing variable. A discrepancy so vast that if she published it, the journal would assume a decimal point was misplaced somewhere in the 900 preceding pages. She runs the experiment again. Same result. The reaction works. The product is correct. Everything observable is fine. And the calculation is wrong by a number that has no name in ordinary language. That is the vacuum catastrophe. Lambda works in every observation we make. The theory predicting its value is off by a factor that dwarfs every other failed prediction in science combined. And now, DESI is reporting that even the observable behavior of Lambda is not what was assumed. What does it mean to build the standard model of cosmology on a term that cannot be derived from any deeper theory, and whose observed value contradicts quantum field theory by 120 orders of magnitude? What does it mean that we named the unknown, put it in an equation, watch the equation work, and somewhere in that process confuse the working of the equation with an understanding of what produces it? And what I keep returning to is this: Lambda is not an explanation of what drives the universe's expansion. It is a very successful placeholder for something we do not understand at all. In 1953, Fred Hoyle walked into a laboratory at Caltech and made a prediction that had no business being right. Hoyle was working on the problem of how heavy elements form inside stars. Carbon is the bottleneck. Without it, the chain of nuclear reactions producing oxygen, nitrogen, iron, and everything else in the periodic table cannot proceed. For carbon to form in stellar interiors, 3 helium nuclei must collide and fuse in a 2-step sequence. The probability of this happening under normal stellar conditions is almost impossibly low. Too low to explain the abundance of carbon in the universe. And yet, carbon is everywhere. In stars, in planets, in every living thing that has ever existed. Hoyle looked at that fact and worked backward. Carbon exists in abundance. Therefore, the reaction rate producing it must be far higher than the raw probability suggests. Therefore, there must be a nuclear resonance state in the carbon-12 nucleus that dramatically enhances the reaction rate by matching the energy of the incoming helium nuclei. He did not calculate this from quantum mechanics. He inferred it from the fact that we exist. He told the experimentalists at Caltech what energy level to look for. They looked. It was there. Not approximately there. Not in the right neighborhood. At almost exactly the predicted value. A value derived from no calculation, no prior measurement, no physical theory. Derived solely from the premise that we are here, and therefore the universe must permit the chemistry that produced us. Think about what that means structurally. A sommelier, blindfolded in a cellar, cannot taste the wine, but he knows the restaurant has been open for 100 years and never once served a table that complained the wine was undrinkable. From that single fact, the restaurant's continued existence, he can predict the wine's minimum quality with precision. The restaurant's survival constrains the wine. Our survival constrains the carbon resonance. Hoyle used us as the instrument. What does that mean? What does it mean that the existence of the observer was precise enough to predict a specific energy level in a specific atomic nucleus? And here is what I find I cannot dismiss. It was a number. Precise. Experimentally verifiable. Derived from our existence. If existence can predict physics, what other features of the universe are constrained by the requirement that we be here to observe them? The gravitational constant, the speed of light, the mass of the electron, the strength of the electromagnetic force, the cosmological constant, 26 numbers that define how reality works at its most fundamental level. Change any one of them and the universe loses the capacity to produce complexity. Not some complexity, all of it. Reduce the strong nuclear force by 2% in either direction. Protons cannot bind into nuclei. Chemistry stops at hydrogen. No stars, no supernovae, no heavy elements, no carbon, no planets, nothing that thinks. Increase the cosmological constant by a factor of a few hundred above its observed value. The universe expands so fast after the initial moment that matter never gravitationally collapses into structures. No galaxies, no stars, nothing. Shift the ratio of the electromagnetic force to gravity by 1 part in 10 to the 40th power. A number whose smallness is difficult to communicate in words. And stars either burn through their fuel in millions of years rather than billions. Too fast for planetary life, or they never ignite at all. Change the mass of the electron by a few percent, and the chemistry of DNA becomes impossible. Change the value of Planck's constant and atomic structure dissolves. Each constant, adjusted individually, breaks the universe in its own specific way. 26 numbers, each sitting at a value that permits complexity, each apparently unrelated to the others at the level of known physics. And together they form an arrangement that allows stars to burn for billions of years, allows heavy elements to form and scatter and recombine into chemistry, allows that chemistry to build structures capable of asking why the numbers are what they are. Picture a combination lock with 26 dials. Each dial runs from 0 to 1,000,000,000,000. The lock opens only when all 26 are set to specific values. Not approximately, not within a range, but exactly. The probability of hitting the right combination at random is a number so small it has no useful analogy in human experience. But here is what makes it stranger than a combination lock. The dials are not set by anyone turning them. They appear to have come preset from the beginning at the values required. What kind of universe arrives with its combination already dialed in? And what does it mean that we are the things the combination was set to allow? What kind of universe produces that specific arrangement? What is the name for a coincidence of this magnitude? 26 independent variables, all pointing in the same direction. And what I find unsettling about this is not that it requires an explanation. It is that every explanation available takes something from you. 3 exist. I am going to give you all 3. And the reason I cannot set this problem aside is that each one, followed honestly to its end, costs you something you probably did not know you were going to have to give up. 3 explanations, in order of how much they ask you to accept. The first is the simplest and the most philosophically empty. In 1974, Brandon Carter formalized it as the anthropic principle. We observe this universe because it is the kind of universe that produces observers. If the constants were different, we would not be here to notice. Logically airtight. Also completely empty as an explanation. Saying we observe a life-permitting universe because only life-permitting universes contain observers is like saying you survived the car accident because dead people don't give interviews. True. Explains nothing about why you survived. Lee Smolin pushed further in 1992. Universes reproduce through black holes. Natural selection favors universes that produce more black holes. Our constants are fine-tuned for black hole production, and life is a side effect. The only option with a testable prediction. Whether the prediction holds is still debated. The second explanation requires you to accept that our universe is one of an enormous, possibly infinite, number of universes, each with different constants drawn from the same inflationary process that produced ours. In a large enough ensemble, every combination gets tried. We live in one that worked. Scientifically motivated, mathematically grounded in inflation, also unverifiable in principle. The third is that the constants are not fundamental. A deeper theory will show their values are mathematical necessities, not free parameters. The most conservative option. The one with the least evidence pointing toward it. Think about the difference between the rules of chess and the rules of arithmetic. Chess rules are contingent. Someone chose them. Arithmetic is not 2 + 2 = 4 in every consistent mathematical system because it follows from the axioms. The question the constants force is whether physical law is more like chess or more like arithmetic. Every option currently on the table says chess. The question is only who or what set the rules. What do you do when every explanation for the most basic features of reality either explains nothing, requires infinite unobservable universes, or invokes a theory that does not yet exist? Which of those costs more? And what I think the structure of this problem is telling us is that the universe, examined precisely enough, produces a question the current tools of physics cannot answer without stepping outside the framework those tools were built to operate in. Inflation was not proposed to explain fine-tuning. It was proposed to solve 2 specific, technical problems with the standard cosmological model. The first problem: the universe looks almost perfectly uniform at the largest scales. The same temperature, the same density in every direction. but regions on opposite sides of the observable universe have never been in causal contact. They could not have exchanged energy or information to reach equilibrium. They are simply identical. The second problem, the geometry of the universe is spatially flat to extraordinary precision. The curvature parameter measured from the CMB is within 1% of zero. Maintaining that flatness from the earliest moments to the present requires the initial energy density to be fine-tuned to 1 part in 10 to the 60th power. Alan Guth published the inflationary solution in 1981. In the first fraction of a second, the universe expanded exponentially fast, stretching everything into contact before the expansion, then freezing the geometry flat. It worked. The CMB confirmed its predictions. Nobody initially asked what inflation does if it does not stop everywhere at once. Andre Linde asked. In 1983, he showed that in most versions of inflationary theory, inflation does not stop globally. It stops locally, in patches, while continuing elsewhere. The inflating regions generate new stopping patches, each with slightly different physical properties set by quantum fluctuations at the moment inflation ended locally. Those patches generate more inflating regions. The process has no global end. It is self-reproducing and eternal, producing an infinite number of post-inflationary regions, each a separate universe with its own constants, its own value for each of the 26 numbers, its own physical laws. We did not choose the multiverse, we chose inflation. The multiverse came as a mathematical consequence of the mechanism we accepted to explain the smoothness of the sky. What does it mean that the most observationally successful framework in cosmology requires, as a side effect, an infinite number of unobservable universes? What does it mean that the constants we measured with such precision may be local values rather than universal laws? And what I find important is this. We are not speculating toward the multiverse from philosophical preference. The data pushed us here. You hire a contractor to fix one leaking pipe in the wall. To reach the pipe, he opens the wall. Inside the wall, he finds a second plumbing system, entirely separate, running parallel to the one he was sent to fix. You did not ask for the discovery. It came with the repair. Inflation was the pipe. The eternal multiverse is the second plumbing system behind the wall. We did not go looking for it. We opened the wall to fix a specific problem, and it was already there. String theory was supposed to unify everything. One mathematical framework, reconciling quantum mechanics and general relativity. The two most successful theories in physics, each impeccably tested in its own domain, each mathematically inconsistent with the other. The only problem was that the theory required extra dimensions. 6 or 7 spatial dimensions beyond the 3 we experience, curled up at scales far below anything we can probe. The geometry of those extra dimensions determines the physical constants of the resulting universe. Different geometries, different constants. The number of possible geometries turned out to be approximately 10 to the power of 500. That is a specific number, not a placeholder for something large. It is the result of counting the distinct geometrical configurations consistent with the string theory mathematics. 10 to the 500 possible sets of physical laws, possible values for each of the 26 constants, possible particle masses, possible force strengths, each one a valid solution to the same equations. Leonard Susskind called this the landscape. Our universe occupies one point in that landscape. The theory does not predict which point. What does it mean that the most mathematically sophisticated framework ever constructed for fundamental physics produces not one universe but 10 to the 500? What does it mean that the theory of everything contains, as a direct mathematical output, almost everything? And here is what I cannot move past about the landscape. If it is real, then the concept of a law of nature requires redefinition. An architect is commissioned to design one building. He delivers blueprints for 10 to the 500 buildings, each structurally valid, each meeting code, each a coherent design. None of them is labeled as the one you asked for. The theory does not tell you which building is yours. It tells you that yours is one valid option among an effectively infinite set, and that you are living in it not because it was the only one possible, but because it is the one where the plumbing works. That is the landscape. The theory of everything produced a catalogue. We are somewhere in it. If bubble universes are real, they collide. When two bubbles expanding through an inflating background intersect, the collision deposits energy on their shared boundary. What it does is leave a mark. A circular feature in the cosmic microwave background with a specific temperature profile that differs from the surrounding background. This is a testable prediction. The CMB has been mapped to extraordinary precision by the Planck satellite. The question is whether the map contains the signature. There is a feature in the CMB called the cold spot. Located in the direction of the constellation Eridanus, it is a region significantly colder than the average background, large enough, cold enough, and statistically anomalous enough that standard inflationary models produce it by chance in roughly 2% of realizations. 2% is not impossible, but 2%, sitting in a list of anomalies that each individually fall at the edge of expectation, starts to accumulate weight. The cold spot has a specific temperature profile, a central depression surrounded by a ring of relative warmth, that several research groups have noted is consistent with the signature expected from a bubble collision. A neighboring universe that intersected ours in the first instance of cosmic history, depositing its boundary energy on our sky, leaving its fingerprint in the temperature map we have now measured for 30 years. The cold spot has other explanations. A supervoid in the foreground. Statistical fluctuation. The debate is not settled. What is settled is that the feature exists, that it is anomalous, and that one of its valid physical explanations is that we are looking at a scar from contact with another universe. What does it mean that the sky contains a feature a neighboring cosmos could have left behind? What does it mean to look up and see, possibly, the mark of a physics we will never access, a reality running on constants we will never measure? And what stops me here is not the scale of the claim, but its specificity. We are not talking about a vague theoretical possibility. We are talking about a temperature number, a spatial location, a statistical profile. The multiverse, if it exists, may have left something we can point at. You find a dent in the side of your car, parked in a lot overnight. Could be wind, could be another car brushing past, could be any number of mundane things. One of the valid explanations is that a vehicle hit it. A vehicle you never saw, that left no note, that is now somewhere else entirely. You cannot prove that explanation over the others, but you also cannot rule it out. And the dent is real. The cold spot is the dent. Another universe is the vehicle that may have passed through. The argument is not that it definitely happened. It is that it is one of the options physics permits, and that should itself be strange enough to hold. The observable universe is a sphere roughly 93 billion light-years across. Everything we have ever measured, every galaxy, every CMB photon, every baryon acoustic oscillation used to calculate expansion rates, sits inside that sphere. Everything outside it is moving away faster than light can return. Not because the information does not exist, because the information will never reach us. The boundary is physical, and everything we call cosmology was built from data collected inside it. The problem is that we did not build our models as if they were local. We built them as if they described everything. We took measurements from inside our sphere, extracted what looked like universal laws, and applied those laws to regions we cannot observe and will never observe. Think about a marine biologist who has spent her career studying a single lagoon. The lagoon is rich, complex, well documented. She has identified every species, mapped every current, modeled every food web. Her understanding of that lagoon is precise. Then someone tells her the lagoon connects to an ocean that runs for billions of miles in every direction, and that the ocean's chemistry, temperature, and salinity differ from the lagoons in ways her models do not account for. Everything she discovered about the lagoon remains true. None of it describes the ocean. And the fish in her lagoon are responding to conditions set by a body of water she has never measured. That is the position cosmology is in. Our observable sphere is the lagoon. The physics we derive from it may not hold in the ocean. Inflation makes this sharper. Eternal inflation implies our sphere is one patch in a self-reproducing structure, with no global edge and no global physics. The 26 constants are what our patch drew when inflation ended here. Other patches drew other values. The laws we measured are the laws of this address. What does it mean to do physics knowing the sample size is 1? What does it mean that the foundational assumption of cosmology, laws discovered locally apply globally, is exactly what inflation's own mathematics undermines? And I find I cannot get comfortable with where this lands. Everything we know about the universe is true inside a boundary we cannot cross. Describing a region we have no reason to believe is typical of anything beyond it. Look at the cosmic microwave background, and it appears smooth. Temperature variations of 1 part in 100,000, distributed across the sky in a pattern that looks at first like random noise. This smoothness is cosmology's bedrock, the same density, the same temperature, in every direction. It is what allows cosmologists to write down equations that describe the whole thing as a single system. The smoothness is also impossible. The regions of sky on opposite sides of the observable universe have never been in causal contact. They cannot have agreed on a temperature. They have no mechanism for agreement. And yet they agree to 1 part in 100,000. You hire 2 separate painters to paint 2 separate houses. They cannot communicate. No phones, no mail, no shared instructions. You check the finished houses and discover they have painted every wall the identical shade of off-white. The CMB's smoothness is that evidence. 2 sides of the universe that share something they could not have exchanged after the fact. Inflation provides the common origin, but inflation comes with a price. The smoothness of the sky was purchased with a mechanism that produces, as a side effect, an infinite number of universes we cannot see. What does it mean that the feature of the universe we needed most urgently to explain required a solution that generates infinite unobservable consequences? What does it mean that the CMB is smooth for a reason we accept theoretically but have never directly confirmed? And I keep landing on the same uncomfortable place. The uniformity of the sky is the thing that lets us do cosmology. And the explanation for that uniformity is the thing that breaks cosmology's most basic assumption. The standard model of cosmology is built on a flaw. A mathematical prerequisite embedded in Einstein's field equations before a single observation is made. That prerequisite is homogeneity. The universe looks the same everywhere at large scales. Remove that prerequisite, and the equations that produce Lambda CDM do not apply. The cosmological principle is not a prediction the model makes. It is the ground the model stands on. An architect designs a skyscraper assuming the ground is level. Everything, load calculations, foundation depth, stress distribution, is computed on the premise that the ground is flat. Now, find a slope steep enough that the foundation on one side sits 10 meters lower than the other. You do not modify the skyscraper. You reconsider whether the design is applicable to this site at all. The Hercules Corona Borealis Great Wall is the slope. Lambda CDM is the skyscraper. It is a filamentary structure approximately 10 billion light-years in extent, roughly 10 times the scale above which homogeneity is required. Simply too large to exist inside a universe that obeys the cosmological principle. The cosmological principle is wrong, in which case Lambda CDM is built on a false foundation. Or an explanation exists. And that explanation requires physics absent from every model on the table. I find it significant that this anomaly gets less attention than the Hubble Tension, possibly because it requires dismantling an assumption so fundamental that the alternative is hard to contemplate. What does it mean that the largest observed structure in the universe exceeds the size the universe is supposed to allow? What does it mean that the cosmological principle is not a prediction Lambda CDM makes, but a prerequisite it cannot function without? In the summer of 1950, Enrico Fermi was having lunch at Los Alamos, did some arithmetic in his head, and asked a question that has not been resolved since. The galaxy is old enough and large enough that if intelligence arises with any meaningful probability, it should be visibly populated. The sky is silent. Frank Drake wrote the equation on a blackboard at Greenbank, West Virginia in 1961. He was organizing a meeting agenda. Drake listed what the group would need to estimate how many civilizations are out there. Star formation rate, fraction with planets, habitable conditions, probability of life, intelligence, technology, average lifetime of a transmitting civilization. Multiply them together. That is n. Drake's original estimate was around 10. It was a guess dressed as an equation. Now Webb is measuring some of those factors directly. Kepler data puts planetary system frequency high. Most sun-like stars have planets, around 1 in 5 with something in the habitable zone. Webb detected water vapor, carbon dioxide, and sulfur dioxide on exoplanets. Every factor Webb can touch has moved the equation toward a larger n. Every factor Webb cannot touch, whether life arises, whether intelligence survives long enough to transmit, carries all the explanatory weight for why n is apparently 0. Think about an accountant auditing a company. She can verify every item on the revenue side. All of it checks out. But the company keeps posting losses, attributed to operating costs, unitemized, unverifiable, simply large enough to erase whatever the revenue side produces. The Drake equation works the same way. The revenue side is being audited by Webb, and it is healthy. The loss side is a single, unitemized line that erases it all. What does it mean that 60 years of improving astronomy moved every measurable factor in Drake's equation upward, while the sky stayed silent? What does it mean that the variables doing all the work to explain the silence are precisely the ones no instrument can measure? Whatever kills civilizations is operating entirely in territory where telescopes cannot go. And only the territory where telescopes can go is getting smaller. Robin Hanson published a paper in 1998. The Great Filter. Are we almost past it? The Great Filter is whatever process is responsible for the silence. Whatever step between the conditions for life and the evidence of intelligence is so difficult that the galaxy is empty despite being old enough to be full. The question is not whether the filter exists. The silence requires a filter. The question is where it sits relative to where we are. If the filter is behind us, the hard step is something in our past. The origin of life, the emergence of complex cells, the evolution of intelligence. We are among the rare successes. This is the comfortable version. If the filter is ahead, the hard step is something we have not yet attempted. The galaxy is quiet not because life rarely reaches our stage, but because most life that reaches our stage does not survive what comes next. We are not a rare beginning. We are a typical civilization approaching a typical end. What does it mean that the more habitable the universe appears, the more dangerous our position becomes? What does it mean that the silence is loudest to the civilizations closest to whatever causes it? And I find it genuinely difficult to hold this thought. Fermi asked his question as a puzzle about the past. Webb is turning it into a warning about the future. Watch a marathon. 100,000 runners start. At the finish line, almost none. The filter is a specific place on the course where something breaks most runners. If you are at mile 5 with a full field around you, the filter is probably ahead. Every additional habitable planet Webb confirms is another runner still in the race at mile 5. And mile 5, with a full field around you, is precisely the worst place to feel confident about the finish. I find this the most personally confronting implication of everything Webb has shown us. The telescope was built to reveal the past. In 1972, Jacob Bekenstein was a graduate student at Princeton, thinking about black holes and a problem that seemed at first to be an accounting problem. The second law of thermodynamics says entropy never decreases, but black holes appear to violate this. Drop matter in, the entropy of that matter vanishes behind the event horizon, apparently destroyed. Bekenstein proposed a resolution stranger than the problem. Black hole entropy is proportional to the area of its event horizon, not its volume, its area. Information is written on the boundary, not stored in the interior. Stephen Hawking confirmed this and established the formula. I find it significant that Bekenstein was not trying to rewrite what space is. He was trying to save the second law. The implication arrived because the math required it. In 1997, Juan Maldacena showed this equivalence is not just a property of black holes. A specific theory of gravity in a curved spacetime is exactly equivalent to a quantum field theory living on the boundary of that spacetime. Not analogous, mathematically identical. The correspondence is called ADS/CFT, verified across thousands of papers over nearly 30 years. What ADS/CFT says, taken seriously, is that gravity is not fundamental. Space-time geometry, the curvature that holds galaxies together, bends light, defines distance, is not a stage on which physics happens. It emerges from physics happening. Space is not a container, it is a consequence. Compare this to temperature, real, measurable, causally effective, but not fundamental. It emerges from the collective behavior of particles and would not exist if you described each particle individually. A DS/CFT suggests space is like temperature, emergent from quantum entanglement between degrees of freedom that do not themselves live in space. I find this the most structurally strange result in theoretical physics. Not because it is speculative, but because it means the medium we exist in is not a given. What does it mean that space is not fundamental but emergent? What does it mean that the question, what is the universe made of, has an answer that does not include space as an ingredient? Stephen Hawking spent 30 years being wrong about information. In 1974, he showed that black holes emit thermal radiation, a quantum effect near the event horizon that slowly carries energy away. Given enough time, the black hole evaporates completely. Thermal radiation is random. It carries no information about what produced it. If everything that falls into a black hole eventually leaves as thermal radiation, the information is gone, not hidden, destroyed. This violated unitarity, the principle that information is always conserved. Every quantum field theorist working on the problem argued that unitarity was inviolable. The argument ran for 3 decades. The resolution came from the holographic principle. Information is stored on the boundary, so it is not lost when it crosses the horizon. In 2004 in Dublin, Hawking conceded. He found a way to see that information leaks out encoded in subtle correlations in the Hawking radiation. In principle, recoverable, in practice, incomprehensible, but not destroyed. He paid off a bet with John Preskill, handing over a baseball encyclopedia. The universe does not destroy information. What does it mean that the past is, in a precise technical sense, permanent, not accessible, not readable, but not gone? And what I find genuinely strange is this. The universe is a system with perfect memory. We just do not know how to ask it to tell us. A shredder, for 30 years, was believed to permanently destroy documents. Then a physicist proves the shredded paper still contains all the original information, scrambled into the arrangement of strips, encoded in the microscopic damage patterns, present in a form that is in principle recoverable. The shredder never destroyed anything. It transformed the format. Black holes are the shredder. The Hawking radiation is the pile of strips. Mark van Ramsdonk published a paper in 2010 containing a thought experiment that has not been adequately absorbed by the broader culture. Take 2 quantum systems, A and B. Make them maximally entangled. In the ADS/CFT framework, this corresponds to a connected spacetime, a geometric bridge between 2 regions. A and B are not just correlated. They are connected by space. Now reduce the entanglement. The geometric bridge gets longer, thinner. Reduce entanglement to 0, and the bridge closes. The two regions are no longer geometrically connected. The space between them is not empty. There is no space between them. Removing the entanglement did not move them apart. It destroyed the connection that made apart a meaningful concept. Think about two people in constant contact their entire lives. Now cut all communication permanently. The relationship ceases to exist. What remains are two individuals who once knew each other. Van Ramsdonk's result says space works the same way. Remove the entanglement and you do not get distant space. You get no space. What does it mean that space is not a container but a consequence of quantum correlations? And here is where I find myself at the edge of what I can hold clearly. The universe does not exist in space. Space exists in the universe as a consequence of quantum relationships, not as a container for them. I think Van Ramsdonk's result deserves more attention. The space you are sitting in right now is not fundamental. Remove the entanglement and it stops existing entirely. Physics has a pattern. When a small anomaly survives every explanation the existing framework can offer, the resolution eventually costs the framework itself. For 50 years, the orbit of Mercury was wrong. Mercury precesses, its elliptical orbit rotates slowly after each complete orbit. Newtonian mechanics predicts this precisely. When astronomers subtracted the calculated planetary perturbations from the observed precession, a residual remained. 43 arc-seconds per century. Too small to see without instruments built specifically for it. For 50 years, that number sat in the literature without a theoretical home. You are an astronomer in 1870 with this number on your desk. Proposals accumulate. An undiscovered planet interior to Mercury's orbit, called Vulcan. Searches conducted. Vulcan not found. A slight oblateness in the Sun. Measurements attempted. The Sun is round enough. Every explanation within the Newtonian framework produces at least one additional problem. The number just sits there. Homeless. In 1915, Einstein completed general relativity. One of his first calculations was Mercury's perihelion precession. The result was 43 arc-seconds per century. Exactly. Without free parameters, without adjustment. The number that had been theoretically homeless for 50 years fell directly out of a theory built on completely different foundations. Not modified gravity, not corrected Newton, but a reconceptualization of what gravity is. The cost of explaining 43 arc-seconds was Newtonian mechanics. What does it mean that the Hubble tension is 9%, 2 orders of magnitude larger? What does it mean that the early galaxy problem, the DESI result, and the large-scale structure violations are all theoretically homeless right now, in the position Mercury's precession occupied in 1870? I find the Mercury parallel clarifying rather than comforting. It took 50 years to close a 43 arc-second gap. The current gaps are larger. 3 directions exist for post-Lambda CDM cosmology. None have won. The first modifies gravity. Moendi and its relativistic descendants attempt to reproduce Lambda CDM's successors without dark matter. They produce some successors. They struggle with the bullet cluster, 2 galaxy clusters that collided and passed through each other, with their hot gas slowed by electromagnetic drag, while the mass distribution continued forward. The offset is precisely what dark matter predicts, and precisely what modified gravity cannot cleanly reproduce. The second keeps the framework and adds ingredients. Early dark energy shifts the CMB-derived expansion rate upward, reducing the Hubble tension. Models incorporating it close some of the gap. They introduce new tension elsewhere. Every added ingredient solves one problem and creates pressure somewhere else. The third replaces the substrate. Loop quantum cosmology replaces the Big Bang singularity with a quantum bounce. Causal set theory replaces continuous space-time with the discrete structure at the Planck scale. Not adjustments to the standard model, replacements for the space-time manifold on which the standard model is written. not yet complete enough to make the full range of cosmological predictions. Picture yourself as a physicist choosing one of these directions. You pick modified gravity, then the bullet cluster data arrives. You pick early dark energy. The matter power spectrum tightens in the wrong direction. You pick loop quantum cosmology. The equations are elegant but cannot yet predict the CMB to Planck precision. Each direction looks promising until it meets the full dataset. What does it mean that none of them closes all 4 anomalies simultaneously? And what I find significant is what that implies. Whatever comes next is probably not an extension of any of these 3 directions. The resolution comes from outside the frameworks entirely. Webb will keep observing until at least 2041. The launch was precise enough to preserve more fuel than required, and each year of additional operation extends the scientific return on the $10 billion investment. It detected water vapor, carbon dioxide, and sulfur dioxide in the atmosphere of an exoplanet. It imaged the most distant individual star ever observed, a blue supergiant at a redshift of 6, existing when the universe was less than 1 billion years old. Each of these results was a test. Each came back with something the model did not predict. Think about a doctor who orders a series of tests expecting to rule out a rare condition. The first test comes back unusual. The second unusual in a different way. The third, fourth, fifth, each unusual, each in a different direction, all together forming a pattern that no longer looks like coincidence. Webb is that series of tests. Each individual result has alternative explanations. The accumulation has a shape. The shape is not the shape of a healthy Lambda CDM universe. You are living in the middle of this. The telescope is running. The anomalies are accumulating in real time. What does it mean to live in the period between when the old answer is known to be insufficient and when the new answer has arrived? And what I find genuinely strange is this. We are not before the revolution, unaware that one is coming. We are inside the uncertainty, with enough understanding to see the shape of the problem clearly and not enough to see the shape of the answer. Webb keeps returning results that do not fit. Massive early galaxies in 2022 and 2023, atmospheric chemistry on exoplanets, and underneath all of that, already running before Webb launched, the Hubble Tension, DESIs, Dynamical dark energy, the Great Wall. Each result has alternative explanations in isolation. The sequence does not. Early galaxies at the wrong masses and chemistry. The Hubble Tension, 2 verified measurements that cannot coexist under a single physics. DESI's dark energy drifting. The Great Wall, a structure too large to exist in a universe that obeys its own homogeneity principle. They come from different instruments, different teams, different mathematics. What they share is where they point at the foundational assumptions of the standard model, not its edges, its load-bearing elements. An air crash investigator finds that the engine failed, the instruments failed, and the radio failed, all independently on the same flight. 3 failures do not point at 3 separate problems. They point at the conditions the aircraft was operating in. The anomalies are 3 failures on 1 flight. The environment they share is a cosmological model extended beyond the range it was ever tested in. I find the convergence harder to dismiss than any individual anomaly. A single universe-breaking galaxy is interesting. A dozen is a pattern. What does it mean that the evidence accumulates precisely where the model was least tested? We assumed the physics inside our observable region described everything outside it. The universe is declining, systematically, to confirm that assumption. In 2023, a team at Johns Hopkins published their conclusion. It cannot be done within the existing framework. Not difficult, not requiring more data, cannot be done. That paper sits alongside Labor's universe breakers, Reese's 5 sigma warning, and DESI's drifting constant. 4 independent groups, 4 independent conclusions, all pointing at the same place. The physics we know describes a region, not the universe. The region accessible from our location governed by the constants our bubble drew in the inflationary process. Within that region, the physics is accurate. The equations work. What they are not is universal. Everything outside the boundary where our light can reach is moving away faster than light can return from it. The laws we measured here may not hold there. A cartographer spends 40 years mapping one continent. The maps are extraordinary, precise, verified, correct about every road and river. Then someone shows him a satellite image. The continent is one landmass among 7. Everything on his maps is accurate. None of it describes the ocean. The maps were not wrong. They were local. Lambda CDM is the map of the continent. Webb is the first satellite image. Every link holds. The chain ends not at an answer, but at a boundary. What does it mean that you are sitting inside a region of physics that cannot verify its own universality? What does it mean that the most accurate physics ever produced is accurate locally and silent about everything else? And I think this is where the title resolves. Not our universe does not mean the universe is wrong or alien. It means the universe we described was a local description that we extended globally without warrant. In 1543, Copernicus published a book arguing that Earth moves around the Sun. The resistance was the recognition that accepting heliocentrism meant accepting something larger, that Earth was not special, that our location was not privileged. Each time that realization has repeated itself, what followed was new science that could not have been built on the old assumption. Step 1. Copernicus, 1543. Earth moves. What followed? Newtonian mechanics. The first mathematical description of the universe. Step 2. Hubble, 1924. The Milky Way is one galaxy among roughly 2 trillion. What followed? The expanding universe. The Big Bang. The whole architecture of modern cosmology. Step 3. The cosmological principle. We occupy no preferred location. What followed? Lambda CDM. 30 years of precision cosmology. Step 4 is happening now. Our laws are not universal, they are local. Each time you zoom out on a map, your house gets smaller. Not because the house changed, but because you can now see what it sits inside. You're living through the 4th zoom, and at this magnification, the universe itself is the house. What it sits inside is the question the zoom has opened. What does step 4 produce? The way the previous 3 produced Newtonian mechanics and the CMB power spectrum. I think the pattern is not accidental. Every time physics acknowledged that our position is less central, what followed was an expansion of what could be understood. The data forced the previous 3 steps, and the data forcing step 4 is already in. Start from what Webb showed us and follow it without stopping. Webb found galaxies that the standard timeline cannot explain. That timeline runs on Lambda CDM. Lambda CDM depends on a cosmological constant that DESI's 6 million galaxies show is not constant. A drifting constant means the vacuum energy is dynamical. Quantum field theory predicts the vacuum energy should be 120 orders of magnitude larger than what we measure, the biggest failed prediction in physics. The 26 constants are tuned with a precision random chance cannot produce in a single universe. Explaining them requires either an infinite ensemble of universes, which falls out of the inflationary theory we accepted to explain the smooth CMB, or a deeper theory that nobody has found yet. If the ensemble is real, our constants are local. Local constants mean local laws. Local laws are consistent with the holographic principle. That is consistent with ADS/CFT. Gravity emerges from quantum physics on a boundary. Emergent gravity is consistent with Van Ramsdonk. Space-time connectivity is a consequence of quantum entanglement. Remove the entanglement. Space stops existing. Every link holds. The chain ends at a boundary, the limit of what physics can currently say. A biologist studies fish behavior in a research tank. The observations are correct. Then someone points out the tank is inside a larger tank with different conditions that influence what the fish do. Everything observed is accurate. It just is not the whole story. We are the biologist. Our observable universe is the inner tank. Webb is the first instrument sensitive enough to notice that some of the fish are behaving in ways the inner tank's chemistry cannot explain. Here is what sits at that boundary. A universe that appears to run on universal laws that turn out to be local. A space-time that feels fundamental, but emerges from quantum relationships that do not themselves live in space. And inside all of that, on one planet, in one galaxy, in one bubble, something that notices. Something that builds a $10 billion telescope and points it at the beginning of time and finds that the beginning does not match the model. I do not know what it means that the universe produced something capable of noticing that it does not understand the universe. What I know is that the question Webb opened is not about galaxies. It is about what kind of thing the universe is, and what we do now that we have seen enough to know the answer is not yes. The telescope is still looking, the data is still arriving. And the silence where the answer should be is getting louder, not quieter.